Welcome back, guys. In this video, we are going to talk about this concept of enthalpy once again, and we're going to explore how we can use the experimental technique of calorimetry to actually figure out enthalpy changes for a variety of chemical reactions. So if we recall back to our discussion of calorimetry, we saw that for processes that take place under constant pressure situations, right, we can measure that heat transfer QP using our coffee cup calorimeter, illustrated on this slide. So now what we can do then is take this experimental setup that we've talked about in detail before, and we can now consider a situation where we add to this container, some little reactant molecules, and maybe we'll have two different types of reactant molecules in there, and then can carry out a chemical reaction equation inside of this calorimeter. And we know that under a constant pressure situation, right, that delta H of reaction, the enthalpy change of reaction for whatever reactant we put in here, is going to be equal to that QP term, the heat transfer to constant pressure. In other words, this Q of reaction will give us a direct measure of the enthalpy of reaction. Now, because this reaction is taking place inside of a calorimeter, which is thermally isolating the reaction from the environment, we know that the Q reaction then is going to be negative, opposite in sign to the amount of energy that this solution absorbs. So it'll be a minus Q solution. So to explore how to calculate delta H of reaction, it's probably best to just go ahead and turn right to an example problem. So in this example I'd like to explore, we're going to put magnesium solid and hydrochloric acid into our little calorimeter. So we're going to add both of these guys to our calorimeter, and the following reaction is carried out. You get some H2 gas bubbling out, and you form a aqueous salt solution. And we're told that we need to determine the enthalpy change for this reaction, and we know that if we add 0.158 grams of magnesium with enough HCl solution to make 100 milliliters of solution and put it all inside of our coffee cup calorimeter, illustrated here, and I'm telling you that the HCl is sufficiently concentrated so that we're going to use up all of our magnesium, right? Complete reaction, so magnesium will be our limiting reactant. When we find that the temperature of that solution rises from 25.6 degrees Celsius to 32.8 degrees Celsius as a result of this reaction. Okay, so just from that point right there, because the temperature of the solution is increasing, we know that this reaction must be exothermic. Okay, but we want to take it a little bit further, and we actually want to determine delta H of the reaction as written above here. And we're going to make a couple assumptions. We're going to assume that the solution's density, right, is that of water, 1 gram per milliliter, and that the heat capacity of the solution is also going to be that of water, 4.18 joules per gram per degree Celsius. So with all of these given values, we know C, we know the mass of the solution, we know the change in temperature of the solution. We're going to need to use that to find the energy change, how much heat was absorbed by that solution, and then use that to figure out how much heat was given off by the reaction, and then use the amount of reactants to figure out how much energy was given off per mole of reactants. All right? So let's take this one step at a time. If we want to come up with a value for Q of solution, well, we're going to need to use our MC and our delta T terms. And of course, in order to come up with the mass, we need to use the volume of solution and density of solution to get the mass of the solution. Once we have the mass of the solution, we can plug it in right here, use the given value for C and the given values for the final and initial temperatures to arrive at our value for Q of solution. Okay, so it's a positive value. The temperature went up, right? So a positive delta T, which means this solution gained energy. Now, of course, we're inside a calorimeter, so the energy of the reaction is going to be the negative of whatever energy, heat of solution we just calculated. So the reaction is losing energy. It's a negative 3.0 times 10 to the third joules. And so to find our delta H of reaction, we are going to use the total amount of energy that was released during the course of the chemical reaction and divide it by the number of moles of reactant that we had present here. So in this case, we're going to take our initial mass of magnesium, divide by the molar mass, so grams magnesium cancels out, and then we're going to be left with a minus 4.6 times 10 to the fifth joules per mole of magnesium. So the last step then is just to take this final value and plug it in to complete our balanced thermochemical reaction equation. So that's the general approach for solving delta H of reaction using a coffee cup calorimeter. You place whatever reactants you want in your calorimeter, monitor that temperature change using a thermometer, and carry out a procedure very similar to what we just talked about.